Hello everyone. Uh, Welcome to the fourth part of the Introduction to Verilog lesson series. In previous lesson, we looked at hierarchical modeling, which is a key concept that is helpful when designing digital circuits. And also we looked at how hierarchical modeling is facilitated by Verilog with the concept of modules. And today we'll be looking further into these modules in Verilog, and we'll talk about some of the most important components of a module in detail. The content covered in this lesson is related to the chapter 4 in the reference book. So if you want to get additional knowledge or information, you can read the chapter 4 of Verilog HDL reference book. So far, we looked at how Verilog modules are defined and how they can be instantiated in your design. And now we'll look at the internals of a module or the components of a module. By the way, some of these concepts we have covered them in brief, but here we'll talk about them a bit in detail. Just similar to what we did it in last lesson, we will look at the components of a module as well with the help of an example design. So the circuit element we are going to build with Verilog today is an SR latch. More precisely, it's an S bar R bar latch. So now you all are very familiar with this S bar R bar latch, I hope, and you all have seen how you can build it with basic logic gates. Anyway, the circuit diagram for the S bar R bar latch is given in this slide as well, so you can refer to it if you want. If you look at it, it has two main inputs, S bar and R bar, and the outputs are Q and Q bar. The internal construction consists of two NAND gates connected as it's given in the diagram. And now we look at how we can write a complete Verilog module for this S bar R bar latch. So here you can see the Verilog code for the module that models our S bar latch, and we look at the components of this Verilog module. Actually, basic details, like I told you earlier as well, the basic details about components of a module, we already have looked at them in the previous lesson as well. We look at about them in detail here. Here, the first thing you need to do is to give the module a name. This name should be given just after the module keyword, and we have given the name SR underscore latch to this module. Then within brackets, you need to give the ports list of the module. This ports list contains the inputs and outputs of the module. For our SR latch, the outputs are Q and Q bar. The inputs are S bar and R bar. We need to specify all these input and output signals to the module in the ports list. Each of them should be separated by a comma. Now next we come to the internals of the module. Inside the module, the first thing we need to do is to declare each signal in the ports list either as input or output. Since Q and Q bar are outputs, we need to specify that with the keyword output. And since S bar and R bar are inputs, we need to specify that with the keyword input in Verilog. And another thing you should notice is that all these input output signals are single bit wires. They are not multiple bit wires. If they were multiple bit wires, or we call them as buses as well, we would need to specify the size of the bus or the multiple bit wire as well. We actually saw an example with multi-bit ports in our previous lessons example, where we tried to model an adder. and we'll look at some such examples later in this lesson as well. So now once we are done with input output ports declaration, we then need to define the internals of the module using lower level modules. In this particular example, we do this by instantiating gate level modules. So what we are doing or using here is gate level modeling in Verilog. Now we instantiate two NAND gates to achieve our design we saw in the previous slide. And something important you can see here is that these NAND gates we instantiate are inbuilt primitive modules in Verilog. We don't define those Verilog, those modules in Verilog ourselves, because they are already defined and they are primitive modules. Just like we give a name to an instantiated Verilog module, we need to give names to these primitive gate modules as well. In this example, we have given the names N1 and N2 for these two NAND gates. For these primitive gate modules, the first signal is the output of the gate, that particular gate. In this example, this is the output of the NAND gate, and the remaining signals connected to it should be the inputs to the gate. And we'll discuss a little more in detail about gate level modeling in next lesson. So you can learn about these things in the next lesson as well. Anyway, here according to our design, for the output of the first NAND gate, we connect Q. And the S bar and R bar signals are connected as inputs to it. For the output of the second NAND gate, that is N2, we connect Q bar. R bar and Q are connected as inputs to this second NAND gate, N2. Here in module instantiation, you should see that what we are doing is creating an instance from a module and placing it in the circuit while connecting proper signals to it, of course. And since you have been only familiar with software programming languages so far, you might feel like this is similar to function calling that you have seen in those languages. But it is not the case here. So that is an important thing that you should notice. You should strictly note that this is not equivalent to function calling in any way. This is only about creating an instance of a circuit module definition and placing it in our design. Okay, so finally we close the module definition with the end module keyword. So we are done with our design block or the SR latch module, and now comes the stimulus block or the test bench. As I told you in the previous lesson as well, the test bench is also another module in Verilog. So therefore, the components we saw in the previous SR latch module can be seen here as well. The module name is given as top, and there's no input output ports list here, as it does not take anything from the outside world as inputs, and also it does not give anything to the outside world as outputs. Okay, now we come to the internals of the module. As it was with the test bench of the adder module we saw in previous lesson, you can see 4 internal wires and a variable of reg type defined for the purpose of giving inputs and outputs to the module to be tested. Then we create an instance of an SR latch module to be tested. Uh, with this, we can test the functionality of it by stimulating different input conditions. Then we have to connect the input output variables we declared above to the SR latch we just instantiated. The signals Q and Q bar are connected to the outputs of the SR latch. And next, since we are going to use variables set and reset to set and reset the latch respectively, we have to feed the inverted set and reset signals to our S bar R bar latch. That is one thing that you should notice. So with this, when you make set equal to 1, the inverted set signal connected to the latch becomes 0. This will cause the Q output to go high, which means the latch is set. Similarly, when you make reset high, Q goes low. That is the latch resets. So now we are done with instantiating the module to be tested. And now what we should do is to give different inputs to this module we instantiated and observe the outputs. For this, we use an initial block we discussed in the previous lesson. And this type of a behavioral initial block is a common component in a test bench module specifically. So inside the initial block, you can see a system task being used to actually monitor the signal changes. This system task might be new to you because we already have seen the display system task, but monitor system task we have not seen that yet. We have not looked at it yet. So anyway, this the way monitor system task works is different to the way display system task works. So you should know how it works, and we'll see how it works. Now you use the display system task to print out the signal values to the command prompt, and there this printing happened only once at the corresponding simulation time. The monitor task is not like that. It prints a new line to the command prompt whenever any signal given to it changes its value. Now for example, here you can see what we are trying to do with this monitor task is to print out the values of signals set, reset, and Q. Whenever any one of these three signals changes its value, the monitor command puts a new line to the command prompt containing the signal values formatted according to the formatting string given here. How to format the formatting string and all that that is very similar to uh, what you saw with display system task. Uh, so basically what monitor task does is that it monitors the changes in signals and prints a new line when it sees a change in one of the signals given as inputs to it. So also another thing you can notice here in monitor tasks arguments is that we are giving $time as well as an argument. So with this, we try to actually print the simulation time as well, along with the signal values we discussed earlier. So finally, whenever a signal changes its value, a new line with simulation time and the signal values is printed to the command prompt. So after that, you can see we assign different values to the set and reset inputs with time. And when we simulate this test bench, we should be able to see new lines getting printed for each signal change that we are doing here. So now we are done with our initial block and also the stimulus module. So we can now close the module with end module keyword. So here this is a kind of like a recap of what we learned about ports or the terminals of a module. Now, ports provide the interface by which a module can communicate with its environment. For example, the input-output pins of an IC chip are its ports. So you all have seen IC chips when you are doing physical labs. So these ports are similar to input-output pins of a IC chip. The environment uh, or the outside the environment can interact with the module only through its ports. So the IC chips you used in physical labs, you could only interact with that particular IC chip via these input-output ports. Now the internals of a module are not visible to the environment. So with this, the designer gets the flexibility to change the internals of the module without affecting the environment. Of course, given that the interface is not modified, the port interface is not modified. When it comes to a Verilog module, it contains a list of ports, which is optional. As we saw with the test benches did not have a list of ports. This is because it does not exchange any signals with the environment. So it does not need to communicate with the environment. So it did not need to have a list of ports. Therefore, if the module does not exchange any signals with the environment, there are no ports in the list. Here is an example design with a full ladder to illustrate the usage of list of ports. The module top is a top level module that works as the test bench for the header, and it does not do any communication with the environment. Therefore, the module top it does not need to have any ports. The module full add 4, which is our full ladder module, is instantiated inside top module, and this full add 4 module does addition for its environment, and hence it needs to communicate with its environment. Therefore, it needs to have a ports list. So you can see how the module definition starts with the module name and the ports list for these two modules, full add 4 and top. Now full add 4 contains a list of ports with its inputs and outputs, and the module top, it does not have a list of ports because it does not exchange anything with the environment. So we saw that inside the module internals, the first thing you need to do is declaring the ports as inputs or outputs. Here you can see different ways you can declare a port as. You can declare a port as input, output, or bidirectional. So as we already have seen earlier, we can use Verilog keyword input to declare a port as input. And also we can use Verilog keyword output to declare a port as output. Further, something new here is you can declare a port as a bidirectional port that can do both input and output by using the keyword in out. Anyway, the first two port types, input and output, will be the most common or the only types actually you will be seeing and using in designs you see in this course 221. Here you can see an example for ports declaration. Actually, we already have seen this port declaration being done before in previous examples. Anyway, you can have a look at this if you did not understand it properly before. Now here for this full add 4 module, the ports list contains the signals sum, cout, A, B and C in, and we need to click declare them as either inputs or outputs. Now sum is a 4-bit output, so we use the keyword output there. This 3 to 1 syntax is used to declare it as a multiple bit wire or a bus. And then the single bit Cout is declared as output. Then A and B are declared as 4-bit inputs. Cin again is declared as a single bit input. Now we are done with ports declaration for full add 4 module. So now we can go ahead with defining the rest of the module internals. Now another important thing that you should notice here is that all port declarations we did are implicitly or automatically, in other words, declared as wires in Verilog, not as signals of type reg. So if you want to make a particular port behave as a signal of reg type, you need to explicitly mention that or specify that. So you will not anyway come across this situation in this CO221 course, but you will need that when you do designs in behavioral modeling in your CO224 course. Now here you can see how you can connect external signals to input-output ports of a instantiated module. Actually, we looked at this also in our previous examples. In brief, the module that we are instantiating here is the full add 4 module, and we are instantiating this inside the module top. We have given the name FA ordered to this instantiated module, and now we need to connect external signals to this FA ordered module that we just instantiated. These signals that are external to the full add 4 module have been named as they have been named with capital letters. The capital A, B, C in, sum, C out, these are the external signals to the FA ordered module, and these signals are inside the top module. So that is why we call them external signals to the full added 4 module. Now when we are connecting these external signals to the instantiated FA ordered module, we should connect them in the same order as they appear in the module definition, which is given at the bottom of this slide. With this rule, the sum signal should be connected first to the instantiated module, then Cout, more precisely the capital Cout signal should be connected next, and then capital A, capital B, and finally capital C in. This actually is similar to the way you pass arguments to C functions. You have to pass the functions in the same order as they are defined in the function declaration. But as I told you earlier, you should not think of Verilog module instantiations as function calling, because they are two different things. In the figure given in the slide, you can graphically see how signals in top module are connected to the signals in instantiated full adder module. So the signals in top module are the signals external to the full adder module, and they have been connected properly in the same order as they appear in the module definition, just like we discussed a little while ago. So this is all about Verilog modules, and I hope you got a solid understanding about these Verilog modules and how you can define your own Verilog module for a given circuit element. And in the next lesson, we'll look at gate level modeling in Verilog a bit in detail. So see you in the next lesson. Bye.